So let's just begin our session. So, good evening, everyone. Welcome to the week 8, or you can say it is the last summary session for this course, Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. So I am responsible for conducting the live interaction session for this course in this semester. So this will be our last session. It will be like a sort of a summary session wherein we will be discussing, or like we will be revisiting some of the basic concepts for the last that we have learned since the last 8 weeks, and we will also be solving few problems which I think may be a bit more important, and we require some more practice in those concepts. So yeah, so let's begin. So from the week one, I hope since the exams are coming very near, very near. Like I think it is on March 22nd. So starting from the first week, we discussed about what is a waste material, how do you classify the waste material. So and then we discussed about the origins of the waste material, their classification. So any ideas on how did we classify these waste material? Yeah, so mm. So multiple different classifications of the waste material, like hazardous, non-hazardous, degradable, I mean biodegradable, not biodegradable. Then we also classified them as municipal solid waste, and different hierarchies of classifications for this waste material has been designed. So after discussing about that, we discussed about the basic characteristics of the waste material. So wherein we discussed about the physical characteristics like density of the waste material, different types of density of the waste material, then concepts like hydraulic conductivity. So hydraulic conductivity is nothing but it's the ability of the the way is the ability of the waste material to allow the water to flow and seep into the ground. Then its uh, factors affecting the hydraulic conductivity like particle size, fabric, and other stuffs. So in density itself, we also discussed about how do you classify this, how do we characterize these properties. So we discussed about the particle size distribution, and we discussed how it is done using the sieve analysis and other equipments. So after that, we discussed on the chemical characteristics and something on the heating value. So where we saw through something about how to calculate the heating value, what is HHV, LHV, their relationship between HHV and LHV. So what is HHV and what is LHV? HHV is nothing but high heating value, and LHV is nothing but the low heating value. And we also went through a certain relationship between HHV and LHV. Any idea on? the particular relationship. HHV is equal to LHV plus, yes. Yeah, okay. It will have another one term. So number of water molecules produced to the amount of fuel burnt. So then we saw a concept something called as GSV or GH, yeah, GSV, gross calorific value. And how do we determine that gross calorific value? The relationship between GSV as well as HHV, and also on other characteristics properties based on their physical nature. So we discussed about many different things. So we have questions related to that. So we will be discussing that as we go towards solving the questions. Then we discussed on something. Okay, let us go for the questions as such. So here I hope this will be a very familiar picture now for everyone. So can anyone tell me what is this equipment? The one that you see in the right hand side. I guess this was even an assignment question, I believe. Yes, so this is a bomb calorimeter. Let me write that. And what is the principle for this bomb calorimeter? Or before discussing the principle, how does this bomb calorimeter works? Operation operation mechanism or operating principle of bomb calorimeter. Or basically speaking, before that, what is the use? Why do we use a bomb calorimeter for this waste material? What are we trying to obtain by using a bomb calorimeter? Heating value or calorific value, anything is okay. Calorific value of the waste material or of any material of your choice, but since this course is for waste, so we will keep waste material. So the operational principle is very simple. So I hope everybody is able to recollect, but you take your material or your waste material, and then you basically what do you say, you place them in the bomb, is the material that you are going to combust is going to be kept in the bomb with in a pressurized oxygen environment. This bomb will be then submerged in a tank with a known volume of water. So once the bomb is ignited, once you start burning, what happens is the bomb is ignited and then the heat is released. So the heat released by the burning of the material is gained by the bomb as well as that of the water. So due to this heat gained by the bomb and the water, there will be a temperature rise, and that will be detected using a thermocouple, so some sort of a temperature sensor. And using that temperature increase, we can estimate how much heat is gained through the burning of the material. Since we know the amount of mass also, so we will be able to obtain the calorific value of the waste material or of any material of our interest. So this will form the major principle for this bomb calorimeter, that is the heat released by the burning of waste material is equal to the heat gained by the water and the bomb. So this is the main concept that we need to remember, that is, for obtaining the heating value of your waste material, you basically burn the material, and whatever the heat is going to be released by the burning will be something that is gained by the water and the bomb. And since you cannot directly measure the heat, you basically measure the heat in the form of temperature rise. So whether it is heat gained or heat lost is basically measured whether the temperature is increased or dropped, and from there you will be able to estimate how much amount of the heat is released by the burning of your material. So this is quite important because the entire heating value, or if you see waste to energy conversion, the thermal conversion route is basically dependent upon this bomb calorie concepts. So and to be and to clarify once again, the heating value or calorific value of the waste material is nothing but the amount of heat that is generated by the material for every gram of material burnt. So this is about the bomb calorimeter. And so as far as the conversion route is concerned, or the course is concerned, we are specifically interested in knowing how to convert the waste material into energy. And for that we have, as we keep discussing this in every week, we have three different routes. First one is going to be your thermal conversion route, second one is the biological, and the third one is the chemical conversion route. So in case of the thermal conversion route, it is basically you're going to use temperature or heat as a source for conversion. And depending upon certain conditions, this thermal conversion route is classified into three different types. I hope everybody is able to recollect. First one is the incineration or combustion, second one is the gasification, and the third one is the pyrolysis. So that's what this table talks about. So if your oxygen to coal ratio, or if your air to fuel ratio, as such speaking, if it is greater than 2.5, then, or if you are going to do your burning process in an excessive supply of oxygen, then that particular conversion process is called combustion, because you are going to supply excessive amount of oxygen for burning your material. And since you supply excess amount of oxygen, the end products what you can expect will be carbon dioxide, water, and the extra oxygen which is not utilized in the process. Suppose if you are going to use the same concept, but if you are going to supply with a limited supply of oxygen, let's say that air to fuel ratio or O2 to cold ratio here is within 0.68 to 2.5 percentage, then you call that conversion process or the thermal conversion process as gasification. So in gasification, you can expect carbon monoxide also, apart from carbon dioxide, hydrogen, and water. The presence of the carbon monoxide is inevitable because you're going to use less, or uh, you know a controlled amount of oxygen for your burning process. And this is the place where you will be obtaining the syngas. So syngas is nothing but, so gasification process produces syngas. So syngas is nothing but, it's also called synthesis gas. So it's a combination of carbon monoxide plus hydrogen gas. So in the place of, so if you're going to use entirely oxygen as your air, like for burning, then you can call that process as syngas, or whatever that you're going to generate, carbon monoxide plus hydrogen as a syngas will be the final product. But if you replace oxygen and use air, then you will also have nitrogen quantity present in them, some amount of nitrogen percentage. So in that case, you can call that as a producer gas. So composition of the producer gas will be predominantly carbon monoxide plus H2 hydrogen gas plus N2. So this is for the gasification process. And in case of the pyrolysis process, as everyone knows, here we do it in a limited supply of oxygen, like very very deficient supply of oxygen, where if you see your O2 to coal ratio or air to fuel ratio is less than 0.68 0.68 fraction. So in that case, your combustion products will be carbon monoxide and hydrogen, as well as you will also be getting carbon in the form of soot or some sort of a solid, mainly soot. So yeah, so this is the three different classification, and it is one of the most important aspect for this course, I believe, because what is the um, what are the three different conversion process of each of the thermal conversion routes, and how they are differentiated from one another. So after this, we basically, so depending upon the, so these are the gas constituents, and then depending upon the harmful nature of these gas constituent, we usually filter out the harmful ones away. Like we usually filter the harmful ones before sending the products into the atmosphere. So this is about the thermal conversion routes. But for the combustion process as such, if you see, for successful combustion to take place, we typically discuss about three different parameters or three different performance factors that are called as three T's. So I think we discussed about this as we were discussing the course also. So any response on what are the three performance factors that are responsible for the successful combustion to happen? The three performance factors for any successful combustion process. I guess I got something. Oh, so time, temperature, and turbulence. So you need to provide sufficient time, sufficient temperature, and sufficient turbulence for the combustion process to be successful. Time temperature is fine, but what is actually meant by the turbulence, or how turbulence as such is a factor determining this combustion process? So any idea on what is turbulence? Like the three T's, time temperature is fine, but what about turbulence? Just a second. So turbulence is nothing but, so for the successful combustion to take place, oxygen should be more. So by providing more turbulence, what you can do is the amount of oxygen that is surrounding that particular area can be enhanced. So that is why, so that is the reason why turbulence is an important factor that is, required for the successful combustion of any material as such. So this is about the three performance factors and the different types of conversion process. So for this gasification or the combustion process to happen, we basically go for certain kind of what do you say, system combustion chambers, right? So what are the types of combustion chambers for this combustion process? There are two different types. Fixed bed, fluidized bed. So I hope fixed bed fluidized bed concept will be known to everyone. So in case of the fixed bed type combustion chamber, you again have two different types of fixed bed combustion chamber. So in under this classification, you have one more classification. So one thing is this underfeed stalkers, and another one is something called grate firings. So wherein I hope everyone is able to remember. So grate firings are nothing but you will. So grate firings are the one which basically helps in spreading the waste material uniformly throughout the structure. The waste here is spread uniformly, and the main reason for, and what advantage is that by spreading the waste uniformly throughout the grate, you can make sure that the air flow is distributed uniformly so that the combustion process is efficient. So you spread the waste material evenly throughout the grate, and then you are basically going to supply air. So because of that, what happens is there will be a uniform, you can say uniform distribution of the air throughout the grate. So due to this, the combustion process will be very efficient. So that is one of the major advantages of the grate firing. So since this process is very efficient, there is a key thing to remember here, that the waste material with a high moisture content as well as ash content can also be used in this case of, can be also be used to produce energy through this grate firing systems. Just let me write this here. Waste is spread uniformly throughout the grate. So air is distributed uniformly, which makes the combustion process more efficient. So since the combustion process is becoming more efficient in this case, the materials that you can use, typically speaking, for a combustion process or any kind of thermal conversion route, our main thing is that the main constraint, you can say, is that the moisture content in the sample should be low. The main reason is because the presence of oxygen or the presence of the moisture will eat away some of its energy for the moisture removal. As such, some amount of the energy will be eaten up, so that will reduce the heating value of the system, or it will require more amount of the fuel to burn the material. But since we are using this uniform grating, this condition is kind of is thwarted. So this is about the different types of combustion chambers. So let's move on towards something like different types of questions. So this will be a predominantly more of solving questions rather than uh, like previous session where we will discuss lot on concepts, because we have already finished that and we have to look up on things for the on different types of questions. So that's the reason, and I have also repeated certain questions. The major reason being is these are like will help in revising the concepts also. So the first question is, which among the following densities include both the pores as well as that of your interparticle spaces in the system? Any response? So this is a relatively simple question. So okay, let me just write the definition for every type of density and then we can match with the answer. So, true density is something that is dependent only on the density of the material that you are taking. So, that kind of excludes both your pores as well as interparticle spaces present in them. This is the only density which the true density, or you can also call it as an absolute density. So is something that only typically talks about the density of your material that you are going to take and not anything related to the pores or the interparticle spaces which is present in your system. Apparent density as such is something different. Here it actually includes the pore volume but excludes your interparticle spaces. So pore volume is included, but then the interparticle spaces, that is when you are going to package your material, the spaces that gets generated, or that spaces is actually going to be neglected while calculating the density of the material or of the waste material you are going to take under consideration. Envelope density is nothing but it's similarly an alternative to the apparent density. So it includes the pore volume, but excludes interparticle spaces. So true density and absolute density are like kind of synonyms to each other. Apparent density and envelope density are same. Bulk density is something which not just only includes the density of your material but also takes under consideration both the pores and the interparticle spaces in the system. So, speaking of which, the answer will be the first one. I hope no confusions here. It's just for everyone to revise on the basic characteristics, the physical characteristics of the waste material in your system. So, next we will go towards third question before coming towards the second one. Winkler's method is used for the measure of which, just a sec. So Winkler's method is used for the measure of which particular parameters? pH measurement, conductivity measurement, dissolved oxygen measurements, and none of the above. So this particular part, dissolved oxygen. Oh, I mean, some other answer was told. Okay, so answer is dissolved oxygen measurement. Okay, yeah. Option C, dissolved oxygen measurement. So the thing is, what do you actually understand when you talk about dissolved oxygen or this Winkler's method as such? How does it help us in determining the dissolved oxygen content in the samples that you take? So the procedure on how do we determine the dissolved oxygen in the water? iodometric type. Yeah. Hmm. Yeah. So that is. Hmm. 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 DO dissolved in the, I mean, the DO present in the system. So first what we do is we basically take this Mn2 plus, and then we basically add it to the system, which basically has the dissolved oxygen present in them. So that will give you manganese oxide. So it will be a sort of a brown precipitate, and this manganese oxide will be made to react with your iodide ion. So 2I minus plus 4H plus. So this will basically result in the formation of Mn2 plus. Again, the manganese oxide is going to get reduced, and the iodine is going to get oxidized to form iodine I2, or elemental iodine you can say, plus 2H2O. So this liberated iodine, as somebody rightly said, is going to be, titrated against the sodium thiosulfide. So you are going to make this iodine react with the sodium thiosulfate, Na2S2O3, gives Na2S4O6 plus 2 iodine ions. So once we basically titrate this, so we can get the number of moles of iodine, number of moles of I2 liberated. So from there we will be able to get the number of moles of dissolved oxygen, or DO, present in the system. So this is basically, this method as such is called as a Winkler's method. And in order to do this, we basically use the measurement is typically done using a membrane electrode method. So there we have a gold as a cathode and silver as an anode, which is basically submerged in a electrolyte, which is separated using this gas permeable membrane. So we basically determine the amount of oxygen transferred through the membrane as a function of the partial pressure of oxygen. So so this is the membrane electrode method. Gold as gold as cathode and silver as anode. So using that, and with a gas permeable membrane. So the transfer of oxygen through this membrane is taken as a function of the is measured as a function of the partial pressure of oxygen, and from here we will be able to determine the percentage of the dissolved oxygen. So there will be certain kind of reactions going to happen in the anode, and some reactions in the cathode, wherein this oxygen is going to react to form OH minus ions, which will be taken up in the so it will form the OH minus ion. So the resulting current in the entire circuit will be calculated, which will form as a parameter to determine the amount of dissolved oxygen within the system. So this is C, and then let's talk about, okay. So the next question is the second one. So this one is done. Second one, which of the following methods are used for sulfur detection? Choose the most suitable option. So you have colorimetric method, big bond combustion, X-ray fluorescence, and all of these. I guess this is also an assignment question only. All of these. Okay. And can you explain? Can anyone explain what is big bond combustion? Big bond combustion. So please check this out. I'm going to mark it in red. And so, which of the following is not the advantage of a screw reactor? Continuous process, better mixing property, ease of scale up, and none of the above. Ease of scale up. So, so screw reactors as such is difficult in scaling up. So this question also I'm going to mark it. Let's discuss this at the end because I need to discuss what is a screw reactors first. So let's move on to the next one, but we'll discuss this towards the end. Which of the what is the type of scrubber as shown in the figure? Spray scrubber, because it is clearly evident that this dry gas inlet, that whatever you are going to take, it actually moves up, and then you have this water inlet which basically act as a spray. They spray over them before that clean, before it enters into the what do you say, mist eliminator and the gas clean out. So this will be your spray scrubber, and whatever that remaining ones are going to be present, like in the dry gas, that particulate matters will actually settle down as a slurry. Spray scrubber. So now these two are again very fundamental. So let's see which routes have a relatively slow rate of energy production from waste. Chemical. But isn't it that the biological routes usually takes a lot more slow compared to chemical? Because in case of the biological roots, you are actually going to use microorganism as a source for the energy generation purpose. So they will, so you have to culture the microbes, allow the microbes to feed on the system, and then energy needs to be produced. So wouldn't biological roots maybe the slower one? So here the answer is biological roots. So actually this question I have directly taken it from your assignment 0. So there is a assignment before all the weeks assignment, you have one assignment 0. So please check that assignment once, because many of us, because since that is not for evaluation, we do not check that, but it's okay. So please check that one also before going for the exam. Now after that, determine the stoichiometric air required to combust methane. 17.16. Okay, wait. I'll just keep this as an answer for the time being, but let's solve it and check, because I don't know what is the exact answer for this question. So methane is CH4 plus, since we are going to use air, we need to basically take both O2 as well as nitrogen gas also into account. That gives CO2 plus H2O. This is this is the basics of the combustion equation that we have seen. So we just need to balance this equation now. So and plus the excess plus the nitrogen content. And since we basically take air, so air we usually assume, or we basically take it as 80 percentage nitrogen and 20 percentage oxygen, we basically eliminate the rest of the contributions in the air. So either we take it as 80 percentage nitrogen and 20 percentage oxygen, or 79 percentage nitrogen and 21 percentage oxygen. So typically the ratio will be very around 3.76 to 4. So here for simplicity in calculation, I'm going to consider air as 80 percentage nitrogen and 20 percentage is going to be your oxygen. So which means it is 4 is to 1. So this equation will be modified like this. Oh, sorry. Yeah. So here we just need to balance the oxygen. So that will be like totally 3 oxygens here. Sorry. Here we will have 1. So 4. So this will be 2 oxygen plus 4 nitrogen. Is this fine? So from here we just need to calculate like what is the total quantity of air, that is 2O2 plus 4 times of nitrogen, that is basically required. Just a second, 1 minute. Okay, so this will be the total air requirement, and for every gram, so this will be totally, if you see, CH4 will be 16 gram per mole, and the entire air requirement will be around 32 plus, just a second, I'll calculate here. So here I think I am making a small mistake. Yeah. So typically here, as per the calculation, it should be something like, so this here we will have it like this. So this should be around 3.76, then only it is matching with the answer. So if you take it this way, then CH4 mass is around 16 grams or 16 gram per mole, and the air is nothing but it will be 2 times of O2 plus 3.76 in nitrogen, so N2, so that will be totally 2 times of 32 plus 3.76 times 28, so which will be nothing but the total is 274.56 grams per mole. So this is for the stoichiometric value. So for every 1 gram of methane, so it's like 16 gram of methane requires 274.56 gram of air. So for every 1 gram of methane, it will be nothing but 274.56 divided by 16. So that is 17.16 gram of air per gram of CH4. So the answer is D. But again, the methodology of solving is this. You just need to write the equation and then take the percentage of air as 79 and 21 and neglect the contribution from the other gases, and then just do the stoichiometric balance, so then you will be able to get this as the answer. So let me just keep it in black. So this is also done. So like this we have one more question, so let's go to that question before coming to this match the following. Yeah, sorry. Develop an equation for the combustion of ethane with 40 percentage excess air and determine the amount of air required for each gram of ethane burnt. So very similar question. We have also solved this question during that particular week session, but over there we used only the theoretical requirement, like that is the stoichiometric coefficient. Here I am saying we are going to burn this in 40 percentage excess air, and for that you need to develop a combustion equation and determine the amount of air required for burning every gram of ethane. So what is the equation and how much is the ethane that is going to get burnt? Same way of solving, but it is just that over there we exactly took that uh, what do you say, the the molar mass of your air. So here it's just that you need to add 40 percentage excess to that before calculating. So I'll just give the skeletal equation. You can balance that out. So ethane is C2H6 plus oxygen plus, let's assume that air has 79 percentage nitrogen and 21 percentage oxygen here. I mean, that's what is a constituent, but let's not keep it as 80-20. gives CO2 plus H2O plus nitrogen. So we need to balance this equation considering the fact that you have 40% excess air. Or balance this equation, then add that 40% excess air requirement for solving this amount of air which will be used for burning ethane. So let me just balance it. So you have carbon 2. So here also carbon will be 2. Then here your hydrogen is 3. So total number of oxygen will be 3 plus 4. So 7. So that will be 7 by 2, or you can take it as 3.5. So here it will be nothing but 3.76 times 3.5. Because yeah, here previously itself I wanted to ask, why is that the nitrogen as such what we are writing in the reaction is coming out in the product? I mean, does nitrogen, whether it does not react with any of the components? So nitrogen is inert. It does not involve in any of the combustion process. Whatever nitrogen you are going to actually supply into your burning or combustion chamber, that same amount of the nitrogen without participating in the reaction is going to basically come out of the systems as well. So that is the reason the number of moles of nitrogen in the reactant side and the product side are same. So now we have come for the combustion equation. So let's calculate the air requirement. So first calculate the moles of air is coming out as 3.5. So mass, or you can say molecular weight, will be of air required. 3.5 times 32 plus 3.76 times 14. Oh, sorry, it will be 28. Yeah. So what will be the value? 3.76 times 28 plus 32 times 3.5. 480.48 gram per mole. So this will be the theoretical air requirement. Now we have to basically calculate 40% excess of that air. So that will be 1.4 times of this 480.48 grams. So that will be, let me use a calculator. 4 480.48 times 1.4, 672.672 grams of air is required for burning, for combustion. So this much amount of air is basically required to burn 1 mole of ethane, which is C2H6, which will be approximately 30 grams, which is 30 grams per mole. Now for every 1 gram of ethane, we have to calculate how much air is basically required for 1 gram of ethane, similar to that previous problem what we solved. So 30 grams of ethane requires 672.672 grams of air. So then how much will 1 gram of ethane require? So that will be nothing but 672.672 by 30. 22.42 grams. So the requirement of air for burning 1 gram of ethane is 22.4 grams of air. 42. So this will be the methodology. So same thing we have followed. It is just that you need to be, the equation should be properly balanced, and we have to calculate the excess requirement. Like, be careful about whether there is any excess requirement given in the question, because if it is 40 percentage excess, 50 percentage excess, then from there we need to actually multiply 0.5 and add to that. Or you can so let me write this properly. So 40 percentage excess, which means 40 by 100. So this will be 480.48 times zero point 0.4. So 192.192 gram of air is required for is required in excess for combustion. So total air requirement will be, total air requirement is nothing but air stoichiometric coefficient, stoichiometric quantity, I'll say better, quantity of air plus excess of air. So that will be nothing but 480.48 plus 192.192 grams, so which will be totally 672.672 grams. So this is the way we solve, and since this was left out, I thought of taking it out, because we at that time we just solved it with stoichiometric coefficient. We did not involve any concept on this excess air requirement. So even in the assignment questions, such questions were not there. So that is the reason I took it today as a thing, as a question for our final session. So any questions on this question? I mean, any doubts or any clarification required? Okay, then let's do one match the following before we start our other questions. So, match the following in the column A and column B. And again, so I would give this as a what do you say, kind of advice that in this question, it is not necessary that column A will match with only one option in column B. There can be multiple answers for the same what do you say. Oh. So one, two, what are the your your responses? TDS, so that will be G. Any other options matching? Okay. Then second one, E. Okay. Third one, okay. Fourth one, solids. Okay. Okay. Hmm. Okay. 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 That's fine. But there are also other, as I said, there can be chances that one column, I mean, one of the rows in column A can match with one or more than one options in column B. So I'll just give one way, like so fourth one, TSS, can go with turbidity meter also. At the same time, TSS means total suspended solid, so it can match with F option as well. So similarly, there is one more which is pending. Yes. Mm. Okay. But again, there is one thing that is missing. So it's something with the column A, fifth row, trace metals. So it is 5H as well as E. So these are the, yeah. So these are the five. What do you say? I mean, everything now I think now it is matched. So this is a kind of a question where you can see, you can match, but match one option to more than one option. So yeah, this is fine, and we have now few more questions to solve. So, okay, let's solve this one. In the yesterday's class, we solved a question on acid value, but we were unable to solve that question on iodine value. So here we are taking up with that question. So you have 100 gram of bio oil sample, which is going to react with 90 grams of iodide monochloride, ICl. After reaction, Ki is added, and the liberated iodine is going to be titrated with the sodium thiosulfate. Zero point 0.3 moles of thiosulfate is going to be consumed to reach the titer value. Determine the iodine value of your oil. So iodine value as such is used for what? I think we discussed this last yesterday also. Iodine value is for what purpose? So degree of unsaturation. So now we are supposed to calculate that. Oh, uh, is it not visible? Oh, So meanwhile, I'll write the reactions. So please keep solving and please let me know the answer. So how to proceed with this solving of this question? That's the initial part. So it's a very simple one. So what does the equation says is that, so this is a balanced equation, I hope so. So zero point 0.3 moles of the sodium thiosulfate is going to be consumed up in the reaction. So for every 1 mole of what do you say, I2, you have just 1 second. So for every 1 mole of I2, 2 moles of thiosulfate is going to be consumed. So which means that for zero point 0.3 moles, how many moles of I2 you will be having is consumed. So the number of moles of thiosulfate that is going to consume is directly related to I2. So which means that for X moles of I2, zero point 0.3 moles of thiosulfate is consumed. So is it 0.15? 0.15 moles of I2 is liberated. So that if you convert that into mass, then mass of I2 liberated will be, or used up, you can say, or liberate. Again, that I2 that is going to liberate, you are going to titrate it with you are going to do titration with the sodium thiosulfate, so that's fine. So 0.15 times I2, the molecular weight is 253.8 grams per mole. So what will be the value? 38.07 grams of I2. Is this fine or any other answers? So we have been given that 90 grams of iodide monochloride, that is ICl, is used up. So if you see for ICl and I2, the molar ratio is 1 is to 1. So which means that from here we need to calculate how much I2 is going to be liberated out from the reaction. So that will be nothing but, so for every 1 mole of ICl you are going to get 1 mole of, sorry, Ki. which means, mm, let me just calculate the molecular weight of ICL. So ICL is 162 gram, and KI is, wait a minute. It's my bad. So what answers are you guys getting? Any answers from your side? Yes, I will deal with this question. I have one small confusion. So meanwhile, we will discuss. Wait a minute. I guess these are all done questions. So yeah, we will discuss this question. So keep just looking at this question. I will see what I'm doing. Some mistake, I believe. So I have to check what is that. So please keep just doing this. This will be some sort of a different question as you we have previously seen. So just try whether it is possible. I think we should be able to solve this, but then please give it a try. So meanwhile, I will just see what is wrong with that question. So this question is simple. You have a biogas plant which is basically constructed for a village with 45 families. You have a the quantity of the waste, that is pig manure, fed to the digester is 400 kg, retention time is 30 days, density is 1200 kg per meter cube. You have to calculate the working volume and the actual volume of the digester, which should be 10 percentage more. Considering the actual volume, calculate the height and the diameter of the digester. Height of the digester is going to be 2 times the diameter of the digester, and here you can assume that the digester is entirely cylindrical in shape. Any ideas on how to progress with this question? Yes, this is so. Let's solve this question. Again, as I asked previously, any ideas on this question? Like how to go about solving this one? So let's read the question once again and solve step by step. We have enough time with us, so no need to worry about that. So the quantity of the waste, that is your pig manure, which is going to be fed to your digester, is about 400 kg. So mass of, you can say, waste fed is equal to 400 kgs per day. Just a second. So weight of the waste So in order to make this slurry, what we are actually going to do is, I guess this is not mentioned in the question, but we need to actually add water to it, and we are actually going to add the same quantity of water as that of the waste material that we are taking. So that will be 400 plus 400, so that will be 800 kg of total slurry per day. So volume of the waste that will be dumped in the, or volume of the slurry that will be going to your digester will be 800 by the density, so that is 12,000 here, which is nothing but 8 by 12 point 6 7, you can take, meter cube of waste per day. So like this, for 30 days this is going to happen. So after 30 days, volume of waste will be, nothing but 30 times this 0.67 meter cube. So that if you multiply, approximately 20. Okay, yeah, makes sense. So that will be nothing but 20 meter cube of waste, or 20 meter, yeah, 20 meter cube of waste in the digester. Now we have calculated how much amount of the waste is going to be dumped inside your digester. So this is going to be your minimum working volume of the digester, and what they have said is the actual volume is going to be 10 percentage more. So actual volume of digester is 20 times 1.1, so that will be 22 meter cube. And since we are taking the digester as cylindrical in shape, so as digester is taken as cylindrical in shape, so we can take this 22 as pi r square h, because we are taking this digester is cylindrical in shape. So with that calculation, it will be 3.14 times d square times h by 4. I'm taking pi r square as pi d square by 4 times h, and it is given height of the digester is 2 times that of the diameter of the digester. So h is nothing but it's equal to 2d, so it will be like this. So this will be approximately equal to 6.28 times d cube by 4. So if you solve this equation, you will be able to get the diameter, and if you get the diameter, you can use the equation that h is equal to 2d. Is that correct? Yeah, h is equal to 2 times diameter. So this one is with this, and yeah, it's now clear. So this is correct. So now from here you will be calculating the I2 as nothing but 90, which is your moles of ICl, times 126.9 by 162.35, so which will be 0.78 times 90. So 70.34 grams of I2 liberated. Now we need to subtract these two. So that will be nothing but 70.34 minus 38.07, which is 32.27 grams of I2. And this is for 100 ml of bio oil. As per the definition of the iodine value, we need to basically calculate the amount of iodine liberated for 100 grams of bio oil or 100 ml of bio oil. So then here iodine value will be, value is 32. Suppose if the question asks for 200 ml of bio oil, then you need to divide this 32.27 by 200. Suppose let's say I am going to make a modification here. If I'm going to use 200 ml of bio oil, then it will be 32 by 2. So in that case, it will be approximately, iodine value will be 16, because 32.27 by 200, sorry, by 2, because it's for every 100 ml of bio oil. So then if it is 16.13, so iodine value can be approximated to 60. So apart from these questions, we have one here and another one here. But since again we are running short of time, so what I can do at what I can do at best is I can give the solution for these two questions when I'm uploading the PPT for this week. So that would be, I think, best, because we are running short of time and I don't want to extend this session too much. So I'll be uploading this the video recordings for both the lectures that was taken yesterday and today by tomorrow, and this PPTs will also be uploaded, so I think that would be better. So any doubts as such? So let me just, so if you have doubts, you can just ask me right now, or then we will conclude the session. Oh, so yes, then let's conclude the session. So thank you everyone for joining all the sessions throughout the 8 or 9, throughout the 8 weeks. So I thank Professor Prasanajit Mondal as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon, as well as as well as this summary session on this week, on this in one of the weekdays. So yeah, thank you everyone for joining. I hope to meet you all in some other NPTEL course. Till then, bye and all the best for your exams, I guess scheduled on March 22nd. Thank you.